Hi, in this video I'm going to show an example of using reinforcement learning to control the house temperature using a smart thermostat. The environment is going to be done in Simulink, which is very convenient for this type of problems. The thermodynamics of the house are going to be modeled with Simscape blocks to model the heat transfer from the windows, roof, and walls. And the heater is going to be a classical control system that is going to be turned on and off by the smart thermostat, which uses the reinforcement learning agent inside of it. So the action space is going to be discrete because it's only two possibilities, turning it on and off. And the observation are going to include the outside temperature, the room temperature, the comfort limits, and the price per watt, in addition to the energy cost, which is computed by the heater. Okay, so let's do the example by clicking Open Live Script, which is going to take us to here. And here is the reward function. Basically, we have the addition of three terms. The reward for keeping the comfortable temperature, the reward, the penalty for taking too many actions. So if the previous action is not equal to the actual action, it means that you switch on or off the thermostat, so you get a small penalty for it. And also the cost for energy spent, so that's the electricity used minus the price per watt of energy. So we get a penalty for cost for and also if you're within the bounds of the comfortable temperature, then you get a positive reward, and a negative one if you are out of bounds, proportional to how much off you get from the limits. So in this case, the addition of these three terms are going to give a positive reward that is accumulated. And also for the signal, it's going to be 0 because we are not going to end because something bad happens. So we just turn it off for this case. So let's say this is the name of the model. So we use Open System to open the model. And in here, so this is the model, and here we have the house thermodynamics model, which is using Simscape as mentioned before. And you can see that this line is for the roof heat transfer, the wall heat transfer, and the window heat transfer. And both of them all of them are going to take the outside temperature. It's going to be one of the inputs, and the other inputs is the heating. So both of them are going to fight each other to get the balanced temperature. So the product of this model is going to be the room temperature. Okay, so the heater is going to control the flow of heat into the house. And you can see that the outside temperature comes from a constant, and this is a data set. So we're going to have a set of tuples and an array of tuples providing the temperature. And Simulink is smart enough to iterate one step at a time through those temperatures, and so we get one temperature value per step in here. Okay, so for the heater, it's going to be a classical control system, and you can see that the heater has its own temperature, a target temperature that is going to be differentiated with the actual temperature from the room, and you have a proportional gain that is going to be turned off. If it is 0, then nothing happens. If it is on, then this goes on. So we have this transfer function here as part of the control system, and then we compute the cost of that energy spent, and this is converted into something that Simscape can understand as a heat transfer. Okay, so the smart thermostat is going to have the reinforcement learning agent as mentioned before. It's going to take as input the room temperature, the outside temperature, the comfort temperature limits, the cost computed by the heater, and the price per watt. And the output is going to be turning on or off the heater. Okay, so we can see here that we got all those inputs being fed. They're going to be packaged. The outside temperature, the room temperature, the comfort limits, and the cost, and the previous action, and the price per watt are going to be packaged into 6 elements that are going to become our observation space for the reinforcement learning agent. So this is the path to the agent, which is the name of the module within the subsystem called Smart Thermostat and RL agent. That's we're gonna use the path to the reinforcement learning block, the name of the model, and the observation object and the action object to create the reinforcement learning environment to train this agent. Okay, so we have this observation. The action is just a scalar with a boolean with two possible values, which are 0 and 1, to turn on and off the thermostat. As mentioned before, we're not gonna use the east-on signal this time, so we're gonna turn it to 0. And the reward this time is gonna be computed with a MATLAB function block that has MATLAB code inside. So the action, we're going to take the previous action, and then we take the even previous action to compare if this was switched on or off, and we can see it in here. Okay, so this is the action and previous action. So if the previous action is not equal to the action, this means that you switch, so you get a negative penalty. You also have the cost, and you have a negative a penalty, negative value for the reward. So we add the reward for the cost, the switch penalty, and if you are within the bounds of the room temperature, then you get a positive reward. So this is your positive reward, but it can be negative proportional to how much you get off the bounds. So you get the negative reward in here if you go out of bounds. Okay, so that's your reward for the agent. So that's pretty simple Simulink environment. So now let's create our agent. The sample time is going to be 120 with the max samples per step of 1000, maximum steps per episode of 1000. So this is the path to our agent as mentioned before, which consists of the model name, the subsystem where it is, and the name of the block. Okay, so we're gonna load actually we can create right now the environment because we have the path. But first, we need to create the observation vector, and also we need the data to feed into a Simulink model, and that's taken from this array, which is basically a data set of temperatures, and we're gonna create a subset. The first part of the array is gonna be for the March temperature, and the last part is for April, after April 15. Okay, so in between, the data in between is this we're going to use for validation, and the data in between we're going to use for training. Okay, so that as you can see here, the temperature data, we're going to assign it to outside temperature, and if you look at the model, that's the name that we expect from the base workspace as mentioned here. Okay, so we got our input data of temperature for the model, and the comfort limits are going to be 23 Celsius and 18 Celsius, and those are also, you can see it in here in the model, that are gonna, those base workspace variables are used there. Okay, so we're gonna create the observation object, which are 6 elements as we saw in the Simulink model. 6 elements, we don't have any bounds. For the case of the action, we're gonna have a discrete space, and that's why we are using a DQN agent in here. The DQN agent, I'm gonna put in the description of the video another example giving more details about the DQN agent. It's basically a neural network that takes as input the observation, and it predicts the long-term reward, and based on that, it just takes the action. In this case, turn on or off the thermostat. So basically, that type of agent expects a continuous observation space and a discrete observation space, so it fits into this type of problem. So you can see that we have 2 elements, 0 or 1, and it is of scalar output. So let's say set the seed of randomization to 0 for reproducibility. The critical options are going to be the learning rate. We only have a 1 neural network in here for the Q to predict the long-term reward, and we're going to clamp the gradient to 1. So the agent options, we are not going to use double DQN. We're going to use the critical options. We're gonna use a buffer experience buffer size, which are the samples that we use for training, and from that experience buffer we sample 64 at a time for updating the weights. And this is the smooth factor because this DQN agent is going to have a target network and a real network, and the target network gets updated with this frequency, and the mesh ratio is this one, so it takes everything from the real network rather than keeping some of the target. Okay, that is explained in the video that I mentioned before about DQN. That is going to be in the description. So this is an argument for exploration, because as usual the reinforcement learning agents want to explore more at the beginning and be more greedy at the end. So that's how you control it. And the initialization options, in the initialization options we're going to specify, notice that in this case we are not creating the neural network for this. By default the DQN agent is going to create a neural network, and basically we're specifying in the initialization that we want to use a recurrent neural network, and in this case understand it's going to be an LSTM. And this is fitting for this problem because we have a sequence of temperature, and this sequence type of problems are good for RNNs, which could be LSTMs or could be GRUs. So we're going to configure to use it an RNN internally. It's going to create the network for us, and number of hidden units for that RNN layer are going to be 64. As for the agent options, we have to specify sequence length, and that's for the observations, which are going to include the temperature. So the sequence is to take advantage of the RNN. So that's the networks that has RNN expects a sequence being fed one element at a time of the sequence to work. So that's why we need that. Okay, now we have the agent options. We have the observation and the action, which is the API, the interface between the agent and the environment, and the initialization options. With that, we create the DQN agent. And then for the agent, we're going to set the sample time, which is 120. And if we update the model now, we're going to see that it is not red. It should not be red. Control D. It takes a while, so I'm gonna pause. So I finish updating, and it's white, it's not red. It's pointing to the agent, which is in the base workspace, so everything is fine. We created our DQN agent. Now let's create the environment, which we could have created before creating the agent. So we had the model, the path to the agent, the observations, and the action. You see that we take the same observation and action between the agent and environment because that's the way that they communicate between them. Okay, so we create our environment. For the reset function, we're gonna use this function given by the example that basically takes the data from the temperature data that we just created in the base workspace. That is gonna be the middle data. And from that, we're going to do some indexing operations and then write it into another base workspace variable, which is called outside end temperature, that is over here, this constant block. Okay, so that's what the reset environment is going to do. So we randomly are going to pick the indexes out of that data in here. So that for each episode, we're going to randomly pick different data set from this temperature data for training. Okay, so that's gonna be a lambda calling that function, and this actually is a method of the environment. So I don't know why they prefer to call it as a function, but it's more clear because the reinforcement learning class is following the object-oriented pattern. So you can see that everything is fine. So for training the agent, we're gonna use 150 maximum episodes, 1000 steps per episode. It's gonna stop when we got a positive reward of 85 or more for 5 straight episodes. So I'm not gonna create these because I'm not gonna train it. But if you want to train it, you just use the train command as any other reinforcement learning example. You pass the agent, the environment, and these training options, so just this, and it's gonna give you the stats. So when you execute this command, you're gonna get this GUI, and you can see at the beginning the reward is terrible and eventually gets to more than 85, and then it stops. You can see here that the reward was 88, and it took 1 hour, a couple of hours, not that bad. Yeah, so I'm not gonna wait that long. So I'm gonna just load the train agent in here. So now my agent in the model is gonna have the weights. You can see that it's gonna be in the base workspace, the agent. It's gonna have the train weights. So now let's test it, and we're gonna test it with the validation temperature. So we're gonna use two data sets. We're gonna use the one from March and the one from April. March is colder than April. So in the reset function, in the validation function, it's gonna be slightly different. It's not gonna randomize. It's just gonna pick it from the validation temperature that we're gonna set in the base workspace. It's gonna take the data and just gonna put it into the same output temperature base workspace, which is the one that the model is gonna read. So we're gonna put that into a reset function and simulate for a maximum set for a 720 steps. So with the simulation options, we call we're gonna call this, which is also a method of the reinforcement learning environment. So I'm gonna call it as such, not as a function. And I'm gonna get the experience, and then this example is gonna have a plotting function. I'm not gonna go into the details. That is gonna take the experience, and it's gonna plot it in 3 different plots using this function. Okay, so now I got the experience from the simulation of the data of March. So I'm gonna plot it, and after notice that when we simulate the environment, the reinforcement learning environment, underneath is doing a Simulink simulation. And notice that we are displaying the room temperature and also the outside temperature and the cost. We're displaying it in this display. So we have this display here. And notice that the temperature is a little cold. And when it is cold, you're gonna see more wiggles in here. And the reason is because you turn on the heater for a while and it gets colder. Turn it on, the heater gets colder. So that happens more frequently. As it gets hotter in here, you see that I turn on the heater and it will stay a while longer. So I don't have to turn on the heater that often. And below you can see the accumulated cost over time. So we're gonna take a look at the plot using the function from this example that I showed. It's gonna use experience. So let's take a look at that. Okay. So here it is. So you can see that this is the same that we saw from the model, and the temperature of the room is within the comfortable bounds. So this is good. It actually is gold there, and the energy is about 6. I can't compare to another relative controller, but I hope that is good. And you can see the switching of the heater. You can see that when it is hot, the switching occurs less frequently, as we observe in here as well. So now let's do it for another validation set, which is for April, which is hotter than March. So notice that I don't have to update the reset function from the environment, because that is going to be pointing to the same workspace variable, which is a validation temperature. I'm just setting it here and just simulate. And then that's gonna execute the model. Okay. Actually had the wrong data, so I had to reload the data, and you can see that the temperature is hotter. So let's just zoom. So we can see here that it's pretty hot. So the room temperature is very stable, and the cost is very small. So let's take a look at the plot. Okay, had to move it. So here it is. So you can see that the outside temperature is hot. So the room temperature That's kind of weird. In the last time I run this didn't happen. So it went above. So it kind of performs well for controlling cold temperature. It doesn't let it go below the cold temperature, but when it goes too hot, it was not ready for that. Maybe the if you notice, the April data set came from the end, and before April everything was cold. So I understand that what happens is that this agent was trained with cold data, so it's not gonna let it go cold, but it does get it a little bit hot, and it's not, actually it's not turning on almost the heater, but this is different. I'm gonna give it another shot. Okay, I reloaded the data. I'm simulating again. So let's take a look. Yeah, now it looks better. So you can see it's more stable. This is the data that I had last time, so it's fine. You can see the cost is not that bad. It's incrementing. Okay, so let's take a look at the plot. Yeah, I just have to reload the data, go back here, and just reload it from the file and assign it back into here. And now let's just use the script to load it. Okay, so let's go for it. Okay, now it makes more sense, and you have the hot data and it's within the bounds, and the cost is accumulating, and you turn it off and off. So it seems that it might have some problems when going out of bounds because of being training with cold data, but at least for this data it's working fine. Okay, that's all for the video. Thank you very much for watching.